Hello, everyone. We're studying some quantum mechanics now. Going to write out the Schrodinger equation, and I have a potential, which you might have seen in the earlier slides of this video, that's called an infinite well. So it's basically a piecewise function for the potential energy U of x. The potential energy U of x will be given by approaching infinity for x is less than 0, approaching infinity for x is greater than L, and will in fact be 0 for x from 0 to L. We're going to solve the Schrodinger's equation for that scenario, and I think you'll see that we have some interesting results coming from it. So let us get started by solving Schrodinger's equation with the boundary conditions. Turn on my document cam. So what I have here is U of x, the potential energy, is a piecewise function. And I'm going to say it approaches infinity for x is less than 0. It's 0 for 0 less than x is less than L. And it approaches infinity again for x greater than L. So that's our potential. And what that means is because this is not just larger than the energy, there's no probability whatsoever that the electron can overcome this potential. So the wave function psi of x will have to be 0 at this point and at this point. That's ultimately what that's going to result in. So we're going to say psi of x equal to 0, which generally we just write psi of 0 is equal to 0, and we're also going to write psi of L is equal to 0. There are boundary conditions, and of course Schrodinger's equation in the area between 0 and L is negative h bar squared over 2m. This is one dimensional, so I don't have to do a partial derivative. It's the second partial of our second derivative of psi with respect to x squared is equal to E psi, and E, of course, is the energy that the particle has. And this again is for 0 less than x is less than L. It's, of course, not even necessary to write the equation for the other parts. So what I'm going to do is I'm going to assume the solution is, in other words, I'm doing an Onsite solution. So let's say let psi of x equal a times the sine of kx plus b times the cosine of kx. Now kx is generally that 2 pi over lambda wave vector, if you will. But right now we're just trying to assume it's going to be anything and then compute the derivatives, plug it into Schrodinger's equation, and then see if that puts any requirements on it, because Schrodinger's equation has to be true for all x. So this means that the first derivative, d psi over dx, is going to be equal to the derivative of sine is cosine, and then of course you got to take the derivative of sine with respect to the argument times the derivative of the argument with respect to x, which is just a chain rule. So I'm going to get k times a cosine kx, and then for this term I'm going to get derivative of cosine is negative sine, so I get minus k times b sine of kx. The second derivative of psi with respect to x is equal to, again, I'm going to take the derivative of cosine. That's going to be negative sine. So now you can see a negative coming out here. I'm going to get another to k. So I'm going to write negative k squared. And you can tell from this that the second derivative is going to put me back where I was on the wave function, except multiplied by negative k. So I'm just going to write this as a sine kx plus b cosine kx. So it's really negative k squared times psi of x. And that's just helpful. I mean, once you take the derivative, you'll see that's actually what it is. I just went ahead and factored it out. So now I can plug it back into Schrodinger's equation, and from that I get negative h bar squared over 2m times negative k squared psi of x I'm going to pull this e to this side, and I'm going to say minus e psi of x is equal to 0. Well, this has to be true for all x. So when I do this, I'll get h bar squared k squared over 2m. That part's positive, minus e squared, or excuse me, minus e times psi of x is equal to 0. Now again, since this has to be true for all x, this must be equal to 0 identically. So this part is equal to 0. And that gives us a condition that must be met. Specifically, k has got to equal the square root of 2me over h bar squared. I could write this h bar out from under the square root, since it would just be a plain h bar since it's under the square root squared, but that's sufficient for right now. So what this gives me is that my wave function should really be psi of x is equal to some a times the sine of square root 2me over h bar squared times x plus b times the cosine of the square root 2me over h bar squared times x. Now this is actually right, but I'm not going to write it that way because we're going to find from the boundary conditions, we're going to find this k is something else, but I will use the fact that k is equal to this to let me figure out what the actual energy is. So now let's evaluate our boundary conditions. So psi of 0 is equal to 0 gives me this. I know that 0 is going to be the left-hand side. Now I got to put in x equals 0. So I get a times the sine of 0, which is 0, plus b times the cosine of 0, which is 1. So this implies that b is equal to 0. So now I've got psi of x is just a sine, and I'll write it in the shortest way, kx, instead of writing that square root stuff. Okay. Now the other part is psi of L is equal to 0. That's going to give me 0 is equal to A times the sine of K times L. Well, we can't do that with the A, or that would make a trivial wave function. That'd make a wave function that basically is just 0, so that's not very helpful. So we have to do it with the KL, and we know that based on the graph of sine, which looks like this, you can say it's going to be 0 at pi, 2 pi, 3 pi, 4 pi, of course also negative pi, so on and so forth. But really we're going to only care about the positive sides. So we're going to say k times L is equal to n times pi, which gives us a neat new expression for k. K is equal to n pi over L, where n equals 1, 2, ... So that's our wave function. The only thing left to do is to normalize it. Let me go ahead and write out the wave function that we know to date. So psi of x is now equal to a times the sine of n pi over L times x. That's our wave function. But in order for it to be a valid wave function, not only does it have to meet the continuity criteria, which is that the wave function has to meet the boundary conditions. That's not necessarily the boundary, the continuity condition. The continuity condition is that the wave function must be continuous, and then the first derivative of the wave function must be continuous. We didn't have to touch any of that. We just did it with this alone. That was sufficient. But the final criteria is that the wave function must be normalized. And what we mean by that is the integral, since the wave function is actually, once you square it, that square of the wave function is the probability of finding it in the interval x to x plus dx. So if I integrate this from negative infinity to positive infinity of psi star psi dx, that must equal 1, because the total probability of the wave function, of the particle that the wave function describes being anywhere in space, has got to be a total probability of 100%. So all wave functions should be normalized. This is called normalization. So really, once you complete the mathematics part of it, there's still a constant. That constant is evaluated by doing normalization. So now we're going to do that. Now, generally speaking, the wave function can be a complex function or a complex number or whatever. So you actually have to take the complex conjugate of it and multiply it by itself. In principle, A could be complex. So I'm going to write it as psi star psi, or excuse me, A star A. But this is clearly not complex, so we're just going to write that as sine squared. So in this case, the normalization condition gives me 1. 1 has got to equal the integral from negative infinity up to 0 of 0 dx, because the wave function really is 0 from negative infinity up to 0, plus the integral from 0 to L of A star A sine squared n pi over L times x dx, plus the integral from L to infinity of 0 dx. That's the total part. That's really what we're doing. Now, the idea is obviously the wave function was 0, so you wouldn't necessarily have to write this, but I wrote it just for completeness. Now, to integrate an actual sine squared, we're going to use an identity, specifically that sine squared is equal to 1/2 times parentheses 1 minus cosine of 2 times the argument. So in this case, I'm going to rewrite this as just A squared, which is a normal notation for A star A, but it also looks like this, the absolute value squared. The 1/2 in the identity I'm going to put out here, and now I'm going to say the integral from 0 to L of 1 minus sine, excuse me, 1 minus cosine of twice the argument. Well, the argument was n pi over L, so I'm going to say 2 n pi over L times x dx. That's our actual integral. Again, that's still equal to 1. So I'm going to say a squared over 2. The integral of 1 dx is just x, and that's evaluated from x equals 0 to L. Now I have minus integral is still a squared over 2, integral 0 to L of cosine 2 n pi over L times x dx. In this case, I'm going to say let u equal 2 n pi over L times x, then du is equal to 2 n pi over L dx. So to make this happen, I have to basically take dx and call it L over 2 n pi du. So I'm going to put the L over 2 n pi multiplied by out front here. So the next step is going to give me here, I just get an L. So this is a squared over 2 times L minus a squared over 2. Now times this will be L over 2 n pi. That's for the change of variables. And I get the integral from x equals 0 to L. I wrote the x there just specifically because remember I changed the variable to u, so it's going to be cosine u du. Well, the integral of cosine u, since the derivative of sine is cosine, the integral of cosine must be sine. So I now have a squared over 2L, and then minus a squared L over 4 n pi times the sine of 2 n pi over L times x evaluated at 0 and L. And I think you can tell, since I put an L in there, I'm just going to get 2n times pi. That's going to be 0. And when I put an x equals 0 in there, I'm going to get 0. So this entire term is going to be 0 minus 0. So that gives us nothing. So what we know is that 1 is equal to a squared over 2 times L. There's really no need to make a complex. We can solve this with a being a real number. And in fact, we're going to do that and let a be equal to the square root of 2 over L. So now we have the normalization condition. Now we know our full wave function psi of x for these boundary conditions is equal to the square root of 2 over L times the sine of n pi over L times x. That's our complete wave function for this infinite well. Now we can also use the fact that the k, which was the square root of 2me over h bar squared, that's equal to n pi over L. So this can actually allow us to figure out how energy is quantized. So from this, we see that if I square both sides, I'm going to get 2me over h bar squared is equal to n squared pi squared over L squared. Or ultimately, we will find that E is equal to n squared h squared over 8m L squared. Notice what happens when I square this. I go ahead and plug in h bar, which is h over 2 pi, and that gives me, since it's squared, that's going to give me a 4 pi squared. So that'll cancel out this pi and end up giving me 4 times 2, which is the 8. So that's where I got the 8 from. So there's the actual energy. We can look at the individual states. Obviously, for n equal 1, it's basically going to be pi over L times x. And when you put in x equals L, you get, of course, just pi times, or just pi for n equal 1. So because of that, you know it's only the first quarter of the sine function. So for the n equal 1 state, the wave function, psi, and actually I should probably subscript this n now since I have an n there, so I can put an n in that wave function. For this one, it's going to actually look like this. At 0 and at L, it'll be 0, so it has to look like that. And of course, what it's doing is oscillating back and forth between these. For n equal 2, we get psi 2 is going to be this. And for psi equal 3, or excuse me, n equal 3, we're going to have this, which again looks like that. Of course, that's psi, but the actual probability is psi squared. So you actually have to square that, and you'd see it'd be slightly different. But that is what the wave function is going to look like. It's going to look like the square of this. So if you square this, that'll actually give you the probability density. Also, if you wanted to calculate, for instance, the probability or the average position of x, you just take psi star, which is just plain psi because there's no complex conjugate here, there's no complex number. You write this and then you put an x and then you put this again, which is just plain psi. Now that doesn't matter whether the x is between or in front of, because these are just multiplications, so I could put the x out in front. But if you integrated x times all this squared, that would give you the average value of x. If you want to know the average value of x squared, you put x squared in there. And you're technically supposed to put it between the psi star and the psi, but that only matters when you're dealing with an operator like a derivative or something. But if you're dealing with just multiplication, then yeah, you can just put it out in front. So if you integrated this squared times x, from x equals negative infinity to positive infinity, which it really is just from 0 to L, that would give you the average position of the particle. If you did it for x squared, that would give you the average position squared, and so on and so forth. The neat thing you can see about this energy, by the way, is the fact that when n equals 1, you get E1, which I should really call that En, just like I did with the wave function. You get E1 is just equal to h bar squared over 8ml squared. So then you see that E sub n is just n squared times E1. So that's another useful thing. So you can see as the n goes up, the energy goes up. So if I double n, the energy goes up by 4. If I triple n, it goes up by 9. If I quadruple n, it'll go up by 16. So that's yet another way of expressing the energy. And this is sort of your first introduction to how quantization affects real particles. So this might be a model, for instance, for a particle stuck in a potential well that it can't escape. A good example would be, for instance, a neutron or a proton in the nucleus of an atom. The nucleus of an atom is being held together by the strong nuclear force, which is the strongest force in nature. So you can sort of assume as a first order approximation that the strength is infinitely strong. Then that would tell you you would expect the energy states for the neutron or the proton to go like n squared, and you expect the wave function to behave roughly like this. And that is a first order approximation to what a neutron or a proton stuck in the nucleus would be. Well, that's basically it. That is a particle stuck in an infinite well. I've also alluded to how you go about calculating average x. Let me write that formula down just so you'll know. So if I wanted to find x average, which is sometimes written x bar, I would write integral from negative infinity, which in our case is from 0 to L, to positive infinity. It's actually 0 from 0 to 0. I mean, from negative infinity to 0, and 0 from L to infinity, of psi star, which in our case is just psi, times x times psi times dx. That's our average value. If I wanted to know the average value squared, I make that squared, so on and so forth. And it's just a matter of, in this case, you could use integration by parts to actually find that. I might do that in a subsequent problem. Well, I hope this helps you better understand how to apply Schrodinger's equation for an infinite potential, and how to find the wave function and know the steps that are required to actually make sure the wave function is complete. Specifically, boundary conditions have to be met, the continuity conditions that psi and the derivative of psi has to be continuous, and then finally the normalization process has to be taken care of.